But today we are going to take a specific example, work it out, and hopefully you can learn from this example and apply what we are going through today to other nonlinear finite element analysis and simulations. The particular example we are going to be talking about today is the partial derivative, not the second derivative, partial x of a particular a times partial u partial x equal to f. And when this a is a constant, or it's something that depends on space but not on the solution, we have a linear partial differential equation to solve. But if the a somehow depends on the solution itself, then we get a nonlinear system of equation. How can we say it is nonlinear? It does not satisfy the principle of linear superposition. It doesn't satisfy because if we have a constant alpha, or let's say just 2, if u satisfies the solution, if I plug in 2u, if I plug in a of 2u times partial 2u partial x, does it equal to 2f? It doesn't, right? So if this a does not depend on u, then actually we can work it out. We can pull this 2 out of the derivative and out of the derivative again. Basically, we get twice the right hand side. But if a depends on u in a non-trivial way, then this no longer satisfies and we lose linearity. Okay, so this is nonlinear. To apply finite element to a nonlinear equation like this, we go through the same procedure. We are projecting the residual of this equation onto a space. We are saying, okay, we want to integrate over the whole domain the residual of this equation, au partial x minus f. This whole thing multiplied with the test function v. The x has to equal to 0 for any v within a particular space. And then this gives us a way to derive the weak form. To derive the weak form, what do we mean by weak form? A weak form requires a weaker smoothness on the solution u because we perform integration by parts. Okay, through integration by parts, we get, let's use the dilution boundary condition and let's assume this is from a to b because we are doing a one-dimensional integration. And let's say u of 0 equal to u of b equal to 0. And of course, you can apply other boundary conditions just as in the linear case. We can apply a natural or essential boundary condition, right? But if we have a essential boundary condition that is equal to 0 at both sides, then we get integration by parts. Then through integration by parts, we get the partial derivative of v multiplied with a of u multiplied with the derivative of u dx. So that's from the first term, and the second term we just copy. It is still our linear functional is equal to 0. So this part is still our linear functional, right? But this part is more complex. We do the same thing. We are going to, so this is the weak form. This is our weak form. Okay, to go from the weak form to finite element, we first of all restrict the space VH. We have to be now in a subspace of X. And UH also has to be in a subspace. And the fact that VH is in a finite dimensional subspace means that we can enforce this equation by enforce a finite number of equations. In order for this equation to be satisfied for any VH, we only need the equation to be satisfied for the basis, for finite number of VHs. And also the fact that UH is within the finite dimensional space means we can expand UH as a linear combination. I have used A here, so I'll use a UI. I goes from 1 to n, a linear combination of these basis functions. And need to enforce VH equal to VI. And once we plug both in, we get integration, and V is going to be replaced by V. We still have A here, but A is applied to UH, which is going to be a summation of that. And then we have partial phi. Let me replace this with J. Okay, so that I don't have a conflict. So this is J partial X, and we also have a summation which can be pulled out over another J. Okay, so actually here I actually have 3 indices, so let me replace this by K. So K goes from 1 to n within this nonlinear function, the function that causes nonlinearity, and then a summation in J that is on this U. The summation in K is on this U. Summation on J is on this U. Okay. So that is going to be the replacement for my matrix vector multiplication. We can still, we have an AJ here. We can still write this as a matrix vector multiplication, right? We can define Aij as this integral here times A but the problem is that A actually depends on U, or depends on A1, A2 up to AN. So we get a nonlinear system to solve. Of course, we can still derive from the linear functional BI, right? BI is still equal to the same thing, is still equal to integration of A and B f times VI of x dx. So basically, we have the problem of we need to solve a linear summation of Aij, which is now a function of the solution A. Okay, times Aj equal to Bi. So J goes from 1 to n. So from a nonlinear differential equation, we derive a nonlinear system. So how to solve this nonlinear system is the thing that the new thing we need to deal with in nonlinear finite element. There are typically 2 ways to deal with this system. The first way is the more rigorous, and it's usually more tedious to derive, but usually works beautifully, is the Newton's method.